Hi, welcome to this tutorial about Monte Carlo simulations. Earlier in this tutorial series, we discussed about the process corner simulations. So this is a continuation of process corner. So if you want to exactly understand what the Monte Carlo simulation is, I refer you, please go through the tutorial tutorials on process corner simulation. So you can see the links here and here for the process corner simulation. And if you are familiar with the process corner and what process corner means and why it is important, and if you are familiar with that concept, then you can come back to Monte Carlo analysis. So it is better to understand, and it will be easy to understand once you are familiar with the process corner analysis. So in the process corner analysis, we started with a resistor saying that uh, suppose we have a resistor R and we manufacture in that in an IC. So the value of R will not be exactly the same as we thought. Suppose we designed a resistor for 1 kilo ohm, it will not be exactly 1 kilo ohm in the chip. It will be slight variation will be there. We analyzed the process corner in detail, and we found the process corners and how to simulate the process corners, and we discussed the reason for process corners also. We discussed the reason for the process variation, like the difference in lithography, the difference in ion implantation, and the difference in diffusion. And because of all these effects, we have the process variations. We started with the example of a resistor, saying that suppose we designed a resistor for 1 kilo ohm. So this 1 kilo ohm will be in the typical corner, and we will have a fast corner and we will have a slow corner. So in the fast corner, the value will be less than 1 kilo ohm. For example, assume it is zero point 0.9 kilo ohm, and in the slow corner, it will be 1.1 kilo ohm. So this is the maximum variation. This is the maximum variation that we can expect in a resistor when we manufacture it. And the process corner analysis enables us to simulate here, and the process corner analysis enables us to simulate here, here, and here. So we can say when we make an IC, uh, when we make a resistor in an IC, how it will behave when it is here, how it will behave when it is here, how it will behave when it is here. So we in the process corner simulation, we simulated it for the extreme different corners. That is the extreme condition, how much maximum it can vary in both the directions. So this is what we explained in the process corner simulation. So we have the typical corner, we have the fast corner, and we have the slow corner. We said it will be 1 kilo ohm. Well, 1 kilo ohm, and in the fast corner it will be zero point 0.9 kilo ohm. In the slow corner it will be 1.1 kilo ohm. And the process corner simulation, we simulated it here, here, and here. But in reality, when you make the IC, it could be anywhere in these lines. It could be here, or here, or here, or here, and it could be anywhere. So how we know the IC will work here? How? What is the characteristics of the IC if it is here? And and what is the cara of the IC if it is here, and we don't know all these things, and we cannot simulate in these points we cannot simulate using the process corner analysis, because the process corner will simulate only here, here and here. The first option that the Monte Carlo simulation gives us is the process variation. That is, we can simulate the process variation in between the corners. So we can simulate it anywhere in between this corner and this corner, or this corner and this corner. So this is the one simulation that is available in the process corner. Sorry, in the Monte Carlo simulation. So when we run a Monte Carlo simulation, so will it be located here or here? So who is determining that? So these points in Monte Carlo analysis, those points are selected in random, or we can give some statistics to select the points. So if we run more number of simulations, we can cover almost all the area in between this point. So these two extreme points. So the number of simulation we are running, the more we will get the samples along this line. So we started with the example of the resistor, and this is equally applicable to any device, like whether it is a capacitor or if it is a MOSFET. So the second option that uh, Monte Carlo gives us to simulate the mismatch. And now let us analyze what is mismatch. Suppose you have two resistors and they are R1 and R2 and they are identical. So you made two equal resistors of suppose you made two equal resistors of 1 kilo ohm, and you did the layout in the IC. You did the layout very close to each other, and their sizes and exact they are identical. In the layout also they are identical. But even after that, if you make the IC and if you measure these two resistors, they will not be exactly same. There will be a small minute variation in between the resistance value and all the characteristics. So that is called the mismatch. So this mismatch is not as severe as the process variation. The mismatch means suppose one resistor is here, another resistor will be very near to this. Because you did the two resistor, you made them identical, and you made the layout. In the layout also you placed them very closely. And if one resistor is here, another resistor will be very near to that. So if you made them identical and if you place them nearby, it will never happen that one resistor is at here and another resistor is at here. This will not happen. We will come back to this point, and we will discuss this in detail when we discuss the inter-die process variation and intra-die process variation. So if you make two resistors of 1K and 1K, and if you make them in an IC, and if you in the IC, this is the IC, you place them very closely, and if you measure, there will be a small difference in the value, and that is called the mismatch. So this is very important because suppose you have a current mirror. So in the current mirror, suppose you have a current mirror and you supply a current I to this current, and you are replicating the current in the two branches. So assume these two MOSFETs are exactly equal, and you made the layout very perfect, and this current is I1 and the current through this is I2. So the I1 will not be equal to I2 in the IC. Even though in the simulation I1 is equal to IC. Once you fabricate the IC and measure the value of I1 and I2, it will not be exactly equal. There will be a slight variation in this. So this is one example of mismatch in the MOSFET, and another and most of the applications you don't like to have this mismatch because you want I1 is equal to I2. And another example is in the differential pair. In the differential pair, the differential input pair, you have two MOSFETs, M1 and M2, and this is the tail current, the DC bias tail current, and here you are applying the input V1 and V2, and you assuming M1 is exactly equal to M2, and you want M1 to be exactly equal to M2 to get a very good performance in the differential pair. But this will not happen. There will be a small mismatch in between M1 and M2. But this is not process variation. This is not process corner. But this is because of the process variation. But this is not as severe as process corner. So when you do the layout of M1 and M2 very closely in a perfect manner, even also there will be a slight variation between M1 and M2, and that is the mismatch. But M1 will not be in one corner and M2 will not be in another corner. So this is a very important point to understand. In any case, it will not be possible that M1 is in the fast corner and M2 is in the slow corner, or M2 is in the typical corner. This will not happen. Both of them will be very close uh, in the corner. If I am calling this fast and this slow and this is typical, both of them will be, we don't know where exactly it will be, but both of them will be close. Both of them may be here, both of them could be here, both of them could be here, both of them could be here. Anywhere it can be, but in between them there will be a small difference, that we call the mismatch. So I think this point is very clear, because this is very important to differentiate between the mismatch and the process corner. So when you make an IC, suppose this is your wafer. In a wafer you will have different ICs. So you can cut the wafer into different ICs, and in this all the squares are different ICs. So in all the ICs I have two resistors. They are placed very near. So this is one resistor and this is another resistor. So these two resistors and so these two resistors I am assuming they are here. So and in the another IC I have the same resistor. It will not be here. It could be anywhere else, and I assume they are here. And another IC, the same design, same IC, but in the wafer its position is different, so it could be near here. So what I want to say is you have to identify the difference between the process corner and the mismatch. Process corner means the difference between this and this. The difference between these two is called process corner differences, and the difference between these two resistors, uh, that is called the mismatch. So this difference between these two is called the mismatch, and difference between these two is called process variation. And the case that will never occur is you will not have you will not get a resistor here which is located here and another resistor here which is located here. This will not happen because in the layout they are placed very closely, so there will not be this much process variation in an IC. So there are two types of process variation. One is the process variation. One is the process variation inside the IC that we call the mismatch, and the process variation between the ICs. It is not inside the IC, it is between one sample to another sample that we call the process variation. So we explain this with the example of a resistor, but it is not limited to resistor. It is equally applicable to any devices like MOSFET, capacitor, BJT or anything. So coming back to the Monte Carlo analysis, Monte Carlo gives us two options. One is to simulate the process variation, and another is to simulate the mismatch. So when we simulate the process variation, assume this is my IC and I have this two resistor here, and when I simulate the Monte Carlo analysis for only for the process variation, both the resistor will be exactly the same. Because I am not considering the mismatch now, I am considering only the process variation. So that means both the resistor will be here, both the resistor will be either here, here, or here. Both of them will be exactly same because we are not considering the mismatch now. And the second option is to consider the mismatch. So if we consider only mismatch and not the process variation, then these two resistors will vary. There will be a mismatch between these two resistors. So if we consider only mismatch, it will not consider the process variation. This it will not consider the process variation. So all the MOSFET, all the components that you simulate will be very near to the typical corner. So all the components that you are simulating will be very near to typical corner. You will get like this two resistor here, two resistor here, two resistor here, and everything will be near to the typical corner if you are not selecting the process variation. So uh, in the in the Monte Carlo analysis, you have this option to select either the process variation or the mismatch alone. So if you select only mismatch during the simulation, all of the simulation will be very close to the typical, but they will differ in between. That is, there will be mismatch in between, but the process will not be different. All of them will be very near to the typical. But Monte Carlo gives you the option to simulate with process variation and mismatch. The third option is to simulate with uh, process variation and mismatch. So if you select this option, we have fast corner here, we have the typical corner here, and we have the slow corner here. It will select the process in random. When we run the simulation for the process variation and mismatch, first it will randomly select a point, and all the resistors in that IC will be placed very near to that. All the resistor in the IC will be placed very near to that process, so that uh, in between the resistor there will be only mismatch. So if you run only one simulation, it will be randomly select one point in this line. So if you run only one simulation, it will randomly select a point, and all the components will be placed very near in this corner. So if you run a second simulation, it will again randomly select another point, and all the devices will be placed in near to that point. That means there will be mismatch in between that devices. If you want an exact result, or if you want to cover all this area, so if you want to cover all this area, you have to increase the number of runs. So generally, even people will run 200 or more than that runs to cover all the area to get the process and mismatch. Before going to the cadence and do the simulation of the process of simulation of the Monte Carlo analysis, we just summarize the points what we analyzed. Monte Carlo simulation, it gives a statistical data uh, about the mismatch and the process variation. And suppose you design an op amp and you need some specification, you give some specifications to the op amp, and you want to know how many percentage, what is the percentage of IC that works exactly like you want. For that, you can give the specification to the Monte Carlo simulation, and you can run 100 or 1000 run. And among the 100 and 1000 run, you can see really among all these combination of process and the mismatch, if the system works, if the system works perfectly, you will get out of the 1000, you will get 1000. So out of 1000, suppose you didn't get 1000, suppose you get 900, then you can see the yield of your design is 90 percentage. But if out of 1000 you got only 100 simulations working perfectly, then your yield is very less and it is only 10 percentage. So the Monte Carlo simulation gives you the estimation of the yield of your design, and it is a, I repeat, it's a statistical analysis, and it randomly picks the mismatch and the process, and it gives you a lot of information that we will cover during the simulation in the cadence. So let us go to cadence and do the simulation of the Monte Carlo analysis.